All right, so last example, cathode ray tube. So they're found in the older TVs. So this example and the next example are probably in a couple of years going to be tough or long memories for some of you. But before flat screens, there was something called the cathode ray tube, and it's still used today in certain applications. But the electron is attracted to an obsolete charged anode. So basically what happened was the electrons were fired at the screen, which is what gave it that color at the front. So the potential difference between the cathode, that's where the electrons were fired from, and the anode, which is what they were attracted to, is a difference of that. So we're talking about potential difference, and potential difference is your voltage. So delta V is equal to 2 times 10 to the fourth volts. We want to find the speed of the electron, so we're looking for a velocity. So vector notation comes in handy here. Gives me the mass of the electron, so we know m. That's 9.1 times 10 negative 31 kilograms, not overly heavy. And we know the charge of an electron. Some of you will have this memorized from chemistry. It's 1.602 times 10 to the negative 19th coulombs. So I'm looking at this, and I have no distance, so I want to make sure I pick a formula that doesn't have R2 and R1 in it. And it narrows down fairly quick. So I'm going to do this through conservation of energy. So this is my total energy before and total energy after. So when I look at this, I need to figure out exactly what I want to deal with here. And when I'm reading through, I'm looking at the potential difference. I know afterwards that we're looking at how fast the particle is moving. So I know on the right side of the equation, the energy is going to be converted completely to kinetic energy. So that's my 1/2 mv squared. Now on the left side, what am I looking at here? Well, I am looking at a change in energy, or the amount of energy it took to get from point 1 to point 2. So I am looking at that last red box that we drew up, because that is what's equal to 1/2 mv squared. The right side kind of tipped off what the left side, my options for my left side were when I'm kind of eliminating my equations. So what is delta E equal to? Well, delta E, we know from previous note, is Q, the charge, multiplied by the electric field strength, multiplied by distance. Well, when I look at my information given for this, I seem to be missing my electric field strength. I also don't know a distance between cathode and anode. So we do know, and I'm going to put, oops, a line under the E and the R here and go off to the side here in green. We know that the electric field strength multiplied by radius is equal to delta V. All right, again from a previous formula. So you can see where if you're going to have any frustration getting through this, it's going to be A, getting the terminology correct, and B, being able to manipulate these formulas and do the correct substitutions. Once you've done that, we have a charge. So let's do a bit of a checklist here. I know the charge, I know delta V, I know the mass. Now I have all the information I really needed, and I didn't need, and it's all stems from just playing with and substituting in formulas. So rearranging this, get V by itself first. I'm going to multiply both sides by 2 to get rid of the half, divide both sides by m, and we'll take the square root of it to isolate for velocity right away. So velocity will equal square root of negative 2, and my charge 1.602 times 10 to the negative 19. Change in voltage was 2 times 10 to the fourth. That's all divided by the mass, 9.1 times 10 to the negative 31. Again, you want to make sure, check to make sure you can use your calculator. And we find that these electrons are being fired at 8.4 times 10 to the seventh meters per second. All right, so extremely high velocity. And there we are. So what's left? I want to talk about an inkjet printer. So some of you are going to be saying in a couple of years, what is an inkjet printer? But for the for the current people, you're going to say, I know what an inkjet printer is. How does it work? Well, the inkjet printer, it uses this concept that we've been talking about. And before I get to drawing what the inkjet printer does, if we have two parallel plates that are charged, we know that there is a uniform electric field inside. All right. If that uniform electric field has a particle fired through it, the path of the particle will follow like that. It'll be attracted or be pushed / pulled toward the negative plate. Now, if we look at the particle as it travels through over here with a free body diagram, we know that horizontally, if we fire this particle, Vx, the acceleration is going to be 0. All right, same as projectile motion. It's going to have no acceleration in the x direction because it's traveling at constant velocity. Now, Vy, velocity downward. Well, Vy, the acceleration is going to not be 0 because as it approaches the negative plate, the attraction grows, so that acceleration is continually changing. So, that being said, we know that the particle will follow that particular path. So let's just sketch up what and how an inkjet printer works. So, underneath here, inkjet printer. We are going to give myself an ink supply. So here's where you plug in your ink cartridge. So you slide that in the slot. It then goes up to, and we're going to simplify this a little bit, a bit of a pump. So it sucks the ink out of the ink supply. That pump then pushes it up, and up here, I'm going to draw a nozzle. So this is your printer head. So the ink gets sucked up, pump pushes it up, and then it fires it through the nozzle. So we're going to go with red ink. So red ink in my supply chamber. So it goes up through the pump, and it comes and gets fired out through the nozzle. What then is what it then is going to pass through is a circular chamber or cylinder, and that is going to be what we call the conductor. The conductor. So in order for this conductor to work, it's attached to your power supply. All right, so it's hooked into the power supply. And what it does is it runs constantly, and it positively charges the ink, charges the ink. So remember, the ink is being fired in small little spheres. That's what it's actually being sent out as. So it's going to go through this conductor, and when it passes through the conductor, it's going to pick up a positive charge. So it might have been neutral before, but now it's picked up a positive charge. On the other side of the conductor is the two parallel plates, positive and negative. So these two parallel plates, maybe I'll draw them a little bit lower here. Okay, it'll look like that, and they too will be hooked to this power supply. All right, so we'll just have it connected like that. The ink particles are going to pass between these two plates. The two plates are going to be switched on and off. So let's put a switch box in. So, switch box. So, and what's going to happen is that switch box is going to be turned on and off. On/off. So the computer's going to send a signal as to we need ink here and we don't need ink here. So what happens is if it's on, you get your uniform field. And in that field, the particle will be pushed, as we said before, or above, downward. If it's pushed downward, what's happening is it's being fired into a gutter, and the ink gets returned to the supply. So this is our gutter / our ink supply. So the ink that we don't want going on the page gets sent back to its source. Okay, so this is for field on. I'm going to change it to blue particles, I guess. If the field is off, then the particle will continue on its trajectory and strike the piece of paper. Oops. So here's my paper. So the ink then continues on its straight path and strikes the piece of paper and leaves ink on it. The benefit to having it positively charged is that paper, you'll know, has a static charge, so it helps the ink adhere to the paper until the ink has a chance to dry. So it's a win-win in terms of charging the particle. So then you have your ink that you don't want going on the paper gets returned down. Ink that you want to strike the paper passes through. So this chamber, okay, the switch box, turns on and off, allowing ink to hit the paper. So this is one application of how charged particles in motion are used in everyday life. So they are used with your ink printer. So if you're wondering how that works, that is the process that's involved for their inkjet printer. And there's many other different applications. So probably what you're looking for on the test, it probably fall in the thinking category, is that it's going to involve the charge plate somehow. So you're just looking at, well, you know, in theory, how do you think it would work? And I'm looking for you to make your best guess at it. Provide me with maybe a creative solution, okay? Something that, in general, the process that's involved. But when you see this whole process, the inkjet printer, I liked it because it's something that most people can visualize, even though most of us probably haven't tore a printer apart. But most of us can visualize what's going on. So some of the particles strike the paper. Well, it's a continuum. That pump, the pump is too slow turning on and off. It can't modulate that ink striking the paper. Okay, much too slow at this point in order to do the control. So that's why the control was moved up to the switch box, because electricity being flipped on and off is virtually instantaneous. So you can make the decision, do I want the particle to go through, or do I want it to go back to my supply down the gutter? And that can happen in the blink of an eye. So there you are. Learned something new today. Something for a dinner conversation tonight. Here are 4 questions for you to work on tomorrow. Between them and the journal, it'll take you the period for sure. If you have any questions or any what ifs, that's the time to ask tomorrow. So anyway, have a good night, and we will see you in class tomorrow.